Okay, so welcome to class 2. Today we will start with materials thermodynamics. I think in the last class we were actually looking at the motivation to actually so study thermodynamics and kinetics of materials in order to be able to efficiently design your growth of your functional materials depending on the final function that you desire. Okay. Now so what is it that we have to study in material thermodynamics? Let's just ask the question before going to develop the language of thermodynamics. Okay. So for example, here I am showing you a technique. So this is called the so called Czochralski technique, and Czochralski is used to, I have a couple of YouTube videos to show, but I am because of copyright issues I will not be able to play it in this, but then you already can see the citation for this, so you can actually play these videos by yourself, but I will not play it in this course. Okay. Now what is Czochralski? So using Czochralski is a single crystal growth technique, and using Czochralski you are able to grow wafers of silicon, right. You are able to grow bulk silicon single crystals, and then you are able to cut slice wafers of silicon as you see in your clean rooms, or so wherever you have seen silicon wafers, right. So how does it work? So first you have so if you can follow my mouse, first you have this vast some amount of silicon. This is what is called polycrystalline silicon, right. You melt it, right. So first you heat it and melt it, okay, in this huge crucible like thing that you have here, right. Then you actually so melt it, meaning you are actually heating it to a this is in a heater sort of an assembly here, right. Then there is a seed of silicon, right. So this seed so you start dipping it inside the melt, right. So the seed goes and sits inside the melt. Okay. Now what is happening? Just look at all the processes that are happening here. First, this is a very hot liquid, some 1000 degrees, 2000 degrees. I don't remember what the temperature is, but it is hot enough such that silicon is a liquid here, right. Then I am putting in some cold material, which is a seed of silicon. Now this seed can also be polycrystalline. It's some kind of dirty silicon, but it is used to nucleate the silicon single crystal that is going to come up, right. So I am going to so put this seed. There is some heat transport problem here, because once I put this seed, I am putting this seed and I am also rotating it for some mechanical uniformity, but so once I put this seed, there is a heat transport problem. This is at a low temperature, this is at a higher temperature. So selectively, if I have a nucleation of silicon, right, so wherever the seed has been dipped, now that is the region where the temperature is also much lower, right. So the instantaneous temperature is much lower. So the silicon, the crystalline silicon or the solid silicon should be able to nucleate there, right, and it nucleates in already existing silicon. That is why the seed is there. Seed is like you do this the curdling, right. So you make curd from milk, so you need that little bit of seed so that the curd nucleates and propagates and proliferates, right. So similarly, you put a seed so that so first of all there is a thermal problem here, a thermal gradient problem, and so locally you are creating a spot which is cold enough for silicon to nucleate. Once the silicon nucleates, you then start sort of spinning it and taking it out, right. So once you are taking it out, this silicon is colder, so there is heat transport problem such that this region starts progressively getting colder and colder, and so my nucleus is starting to grow in this direction. So I am making it grow in a very slow fashion, right. So then eventually I remove it, the entire melt is starting to crystallize, and so I have a silicon ingot that comes out like this, and this silicon ingot I am going to cut it off. The top and bottom are gone because they are in a shape that I don't desire, and the rest of it I am just going to slice it and polish it and do the final polishing to make my Czochralski wafers, silicon wafers. Now what are the concepts? Okay, so this is a nice technologically well developed process, but if you look at all the concepts, first melt, then solidify, right, So melting, solidification, we are talking about phase transitions essentially. You don't always need to melt, right. So in this process you are coming to a single crystal from the melt phase, but you always don't need to melt. You can come from one phase to another phase, a high temperature phase to a low temperature phase, something like iron for example, right. So I can just heat it to a higher temperature phase and then cool it down to a lower temperature phase, right. So and make the wires that which is more ductile, let us say, and then draw iron wires in a shape that I want and then cool it down to a low temperature phase, right. So I need to learn about phase transitions, right. Now this is just silicon transforming to silicon, but yesterday in the previous class I was giving you example of barium titanate coming from barium carbonate, right. You have to do some chemical reactions, right. You have to look at phase transitions, right. And then so there is a heat transport problem that we are not looking at in this course, but other than heat transport there is a problem of how is it nucleating and how is it growing. So that is the problem of kinetics, right. So all these are involved in this entire process of making your silicon single crystals. And finally, why single crystal? Why would it not give a polycrystal? That depends on the rate at which you are pulling this out, right. So you do it very slowly, materials would like to become as single crystalline as possible, right. You do it fast, these defects like grain boundaries etc. come up, right. So there is some rate dependence in how you do it. You do this process very slowly, right. So it's like keeping trying to make a very small baby, putting her or him to sleep, right. You have to be very delicate and only then so it will work, otherwise they will wake up, right. So it's the same thing here. So you have to be very delicate to be able to get a single crystal, right. All these processes, right, are involved, and then each of them comes from thermodynamics or a kinetics, right. So now we are going to develop the language of thermodynamics, but to understand such processes first, and once we understand these processes we can design our own processes, okay. So that's the nature of this, right. So this is the entire video of Czechoslovakia process. If you want to click it and check it, you should be able to. And so there is another process called float zone technique which also is used to create single crystals, so you can read it up, right. So again similar processes, essentially you are melting and from the melt you are sort of drawing a single crystal out, okay. Okay, so so essentially we start with material thermodynamics, and to understand material thermodynamics and how all these processes, how all these material synthesis processes are possible, we need to so we need to develop the language of thermodynamics. As a material scientist will use, right. So I am not going to look at thermodynamics, right. As a material scientist would use, I am not going to look at heat engines, I am not going to look at Carnot cycles and so on, although they are also quite important processes, but then that belongs to the the domain of mechanical engineers, right. So that is not part of this course, okay. Okay, so now in the language of thermodynamics, so what is it, so if I talk about thermodynamics, the first thing that comes to my mind is what is system, what is surrounding. Right, system is everything that I care about and surrounding is everything that I don't care about, right, but that affects the system, right. So for example, okay, so first let us classify it and then let us look at some examples. So what is there are three different types of systems, one called an isolated system, one called a closed system, and the third one is an open system. If you talk to people doing statistical mechanics, they will call this a microcanonical ensemble. They will call this a canonical ensemble, and they will call this a grand canonical ensemble. So same thing, different languages, right. Right. But thermodynamics, the theory of thermodynamics came before StatMech, and then StatMech came to explain more in details, right. So from a very microscopic picture how this theory of thermodynamics makes sense, okay. So they are sisters of each other, so let us not distinguish them too much, but so we are going to look at things from a thermodynamic perspective more or less, okay. Now what is an isolated system? Isolated system is a system, right, where I care about everything, and so this is the system. Let us just call this the system, this the surrounding. The examples are coming, so wait for it. Now, the system, which is the region that I care about, does not exchange. So, no exchange of, this is isolated, no exchange of mass or energy between system and surrounding. Okay. Now, closed system. Okay, so what is an example then? Okay, so let us 1 second, let me erase this. What is an example of an isolated system? I have a system. I have a partition, right. So, these are rough partitions with 4 valves in 4 these are rigid partitions, let us say. So, this is a wall with rigid partitions or a cylinder with rigid partitions, let us say. This side is H2, this side is N2, this side is argon, this side is O2, right. All these are first of all. So, all these 4 together form my system. It is an isolated system, nothing is being exchanged with the surrounding, right. So, I am not supplying any heat, I am not taking away any energy, I am not also releasing all these oxygen molecules and nitrogen molecules into my surrounding, right. So, this is my isolated, all these 4 gases together make my isolated system, right. In the isolated system, so these are, although I call them partitions, right. So, this is a rigid partition, let us, right. This is an example, right. So, this is a rigid partition, and this rigid partition I cannot break it, right. But these other partitions which initially separate these gases, let us say I can use a small hammer or something like that, a robotic hammer, and then break it. Let me draw a hammer here. Okay. So, if I break it, then hydrogen goes into argon, argon goes into hydrogen, there is going to be some interdiffusion. So, a lot of things are happening in this system because I am changing what are called the internal constraints of this system. System dynamics change, everything is happening in the system itself. These 4 gases are something that I care about and how they mix and other things, but I do not care about what is happening outside because there is no so system does not give heat outside and surrounding so there is no exchange of energy or mass, right. So, mass meaning I am not leaking out oxygen, I do not have, this is a well sealed chamber that oxygen is not leaking out, right, or nitrogen is not leaking out, right. So, surrounding I am giving nothing to the surrounding, no energy exchange, no mass exchange with the surrounding. Okay. So, that is an example, right. So, I give this example because very soon I am going to develop this idea of internal constraints, right. So, keep that in mind, very soon I am going to develop this idea of what are internal constraints. Okay. Okay. Then what about a closed system? A closed system can exchange energy between system and surrounding, but no exchange of mass. Okay. Now, to give you an example, let us just say yeah, very naive example. So, again let me give you a magnet or a ferroelectric material, right. So I said ferroelectric material can be switched from up polarization to down polarization, right. So, let us say I have a ferroelectric material with polarization up. So, I apply a battery, right. now my battery, I do not really care about the battery other than applying electric field, applying energy to the system, right. So, this is my system, this is my surrounding is battery plus everything else, or so what it is that it is exchanging energy with, right. So, surrounding is the battery, then I give energy from the battery, right. So, I apply some, okay. So, this is to start with in this polarization, hang on 1 second. Yeah, so let us say I give some voltage, and this voltage or the energy from battery switches the ferroelectric material. So, if this is the initial state, this is the final state, right. So, there is some work done. Okay. So, battery is doing some work on the material. As a result, there is exchange of energy between system and surrounding, and so this is a closed system, right. So, battery is my surrounding and the ferroelectric material is my system. Now, you may also say that, oh, why do not I consider both of them to be my system? I do not really care about the mechanics of the battery, I care about the mechanics of the ferroelectric material, right. So, in this case I do not work on batteries, right. If so I talk to someone who works on a battery, then this can become their system, right. So, this can become their surrounding, right. But you may say, okay, why do not you put both of them into your system, then it becomes an isolated system, that is okay, but then I have to care about everything, right. So, here I do not really care about the battery, so I dump it in the surrounding. The only thing that the battery is used is to maintain the voltage in the system, right. So, apply voltage, remove voltage, right. So, give some electrical energy to the system or remove the electrical energy from the system, okay. So, that is what the battery is doing, okay. Now, so you can have again in our so let us say I have I do not want any, yeah, I mean, so typically I have a reservoir of temperature, right. So, the surrounding is at a particular temperature, the system can be anything that is not really exchanging. So, system is heating up, cooling down, right. Okay, so, reservoir, the idea of reservoir let me come to later, right. So, idea of reservoir let me come to later, but that is an example of a closed system, okay. Now, let us look at an open system. Let me change the color, and turns out open systems are very useful for us, okay. Okay, so I am actually growing a film, a thin film, sorry. Now, how am I growing this thin film? I have a vapor, so thin film of gold, right. So, how do I grow thin film of gold? I have a crucible of gold, right. This is just solid gold. If you went to gold shops, right. So, after I got married, I started going to gold shops with my wife, and you can actually see the melting of gold and trying to understand the purity of gold. They have all these apparatus there to do it. You can actually see that is one form of they are actually identifying the purity of gold, but they also make gold in various forms, fashions, using all these equipment. So you can learn a lot from jewelry shops if well, I'll leave it at that. Okay, so I have a crucible of gold, and this crucible of gold, there is gold inside, and this gold I am heating it with some coils, right. So, I am either resistively heating it or I am heating it with electrons, right. So, in what is called E-beam evaporation. So, once I heat it, I have solid gold that sublimates into vapor gold. This solid gold is bulk gold, it is not in the shape that I want, right. Okay. So I am sublimating, so using a source of electron, right. Here I have a source of electron, some filament, right. So I start heating it using some AC oscillations, and so that actually melts, or even more than melting, it actually vaporizes. There is some vapor pressure of gold that is created. Now this vapor starts flying up, right, and then I put a substrate here. Okay. This is my substrate. So this vapor starts flying up and starts depositing on my substrate. My substrate is at room temperature. So once vapor goes and sticks to my substrate, vapor then it it has to solidify, right. So then again there is vapor gold which solidifies as solid gold, but this time the solid gold will have the shape of a thin film, right. So it's a film of gold that will be coated uniformly on your substrate, right. So that's how you make thin film of gold, and this process by which people make films of gold is called E-beam evaporation, or even so it depends on how you heat the gold. If you heat the gold with some resistive coils, then it is called thermal evaporation. This is a thin film deposition technique, or if you heat it with electrons like I just showed you, that is called E-beam evaporation. Okay. Now what exactly is happening here? Here my system is this thin film of gold. So this is a substrate, and on this substrate can be silicon substrate. I just want to coat a thin film of gold on the silicon substrate. I want to deposit a thin film of gold. So what do I care about? I care about this thin film of gold. So the system is the thin film of gold. Okay. The surrounding is everything else. Right. In fact, let me tell you right away that all this is, let me go to the previous page and say that all this happens in a vacuum chamber. Now vacuum chamber means I remove a lot of gas molecules, but I can control the pressure at which this deposition is happening, right. So pressure is a control variable that I can control, right. So we will keep coming to this idea of vacuum chambers and pressure control, right, and also I can control the temperature of the substrate, although we are doing this at whatever I explained, this is at room temperature, right. So I have some control variables, I have control variables such as pressure, temperature, etc., but so we will come back to that. Okay. But again, coming back to the point at hand, we will keep on coming back to examples like this, right. So as to drive home the point of what is under our control and what is the control of thermodynamics, right. So we will keep on driving that point, but here the thin film of gold that I want to grow is the system. Okay. Surrounding is everything else, and everything else includes the vapor of gold, how you are getting this vapor of gold from that crucible, etc., right. The crucible of gold, vapor of gold, crucible of solid gold, vapor of gold, and all these things, right, and the vacuum chamber, the pressure inside the vacuum chamber, right, all these belong to the surroundings, correct. Now here in this case I am exchanging mass between the film, which is my system, and the surrounding, right. Mass is coming from the vapor getting deposited on the film, right. So the vapor atoms are coming and getting deposited on the film, right. So there is some exchange of mass or exchange of particles between the film and the surroundings, right. But so at every temperature, right, so this is, let us say this is at room temperature, but so at any given temperature I already have some kind of a film. This is a film, this is a substrate. Atoms are coming in, they are sticking, right, but also there is some desorption coefficient, which means atoms also can go out, right. That is just thermodynamics, more atoms are coming in, less atoms are going out. So, overall I have some deposition, right, but it is not as if always the atoms are coming and depositing, there is also some desorption coefficient where the atoms are going out, right. So, there is adsorption and desorption, and that is your mass exchange between system and surrounding. Okay. All right. Now, what about heat exchange, let us say, right. So, I mean again, so the vapor is at a higher temperature, substrate which is a huge heat sink is at lower temperature. Both vapor and substrate belong to the surrounding, right. So, the way we define the problem, vapor is surrounding, substrate is also surrounding, the film is my this is substrate, huge substrate, right. This is vapor, from vapor a hot molecule is coming, hot atom is coming, sitting on the substrate. As soon as it sits on the substrate so it is actually transferring all its heat to the substrate, right. So, my film now is taking heat from the surrounding and giving back heat to the surrounding, to another part of the surrounding, right. So, there is a constant exchange of heat, Q in, this is Q out, right. There is a constant exchange of energy between system and surrounding, right. At this granularity I actually have an open system, because only the film that I am growing is of interest to me, right. I want that to be as good as possible, but that does not mean that I have to ignore the surroundings. I have to know some things about the surroundings, right. I am not completely blind about the surroundings, I have to know something about the surroundings, but the film I am growing, that is my baby. I want to keep that as personal as possible. Okay. So, that is my system. Okay. So, through this example you may have already realized that all the systems, all the more important systems that we are looking at, we will be looking at for growth, right. So, for material synthesis, the important systems of interest for us are the open systems. Okay. So, we have to ideally as soon as possible go to the language of open systems. We need to develop the language of open systems. Okay, good. Now, you have so okay, so that's a system surrounding, that is the first thing that comes to your mind when we speak about thermodynamics. What else? So we talk about state variables, what are called state variables, and the state variables we have used them, the temperature, right, the pressure, something that is that we can control, or something that changes when I change, so something that determines the state of the system, right. So I mean if you learned something about ideal gas, so there is a state equation that relates temperature, pressure and volume of the ideal gas, right. So, volume of the system, right. Then not just temperature, pressure, volume, we have number of molecules, right. So, the number of so in this thin film, right. So, less number of molecules means less thin is the film, or thinner is the film, more number of molecules is thicker is the film, and so on and so forth, right. So, all these, the entropy of the system, the internal energy of the system, all these are what are called the state variables of the system. So, if I say define the state of the system, you should give they will be interrelated with each other, it is not that all of them are independent. But if I give you the address of the system, I should at least give you some of these independent variables such that I know the details of the system, right. So, these state variables tell me something about the address of the system, so that I understand what this system is, right. So, the system barium titanate thin film is at a temperature, or is at a temperature 200 degrees Celsius, pressure atmospheric pressure, and then the volume, etc. And then at that temperature and that pressure, I know thermodynamics is going to tell me that there is one state of barium titanate which is stable, right, which is what is called a stable state, and from that I know that okay, there is a state equation which will, or there should be ideally, right. So, not that every system we know what the state equation is. Ideal gas, the state equation is easy to identify, but there should be a state equation that will relate temperature, pressure, volume. I will know the internal energy of the system because I know exactly how the bonding is, what the defects are, right, and then I will know the entropy, I will know so all the other state variables. Okay. So, at least a few of these state variables will tell me something about the system. The system is barium titanate, all right, I know. Or N for that matter says that there is barium, there is titanium, there is oxygen. Temperature of existence says that okay, at this temperature and given these N's, right, N1, N2, N3, it is this phase of barium titanate, or temperature and pressure, it is this phase of barium titanate that is stable. Then that phase I know what the density is, right. So, that comes from the crystal structure, that tells me the volume of the system, and so on and so forth, right. So, the entire address of the system is known from knowing the state variables of the system. Okay. What are not state variables? Are the work done on the system and the heat that the system is exchanging with the surroundings. Okay. So, the work done, we will quickly look at what this work done and heat is, but then the work done and heat are not state variables. These are they depend on, if a system is at a certain temperature, certain pressure, I know its volume, I know its entropy, and I know its internal energy, right. But if the system is in a certain state, or I know the temperature, pressure, volume of that system, I cannot say how much work was done on it so that I got to that state. I cannot say how much heat was transferred to that system so that I got to that state, right. So, these are called path variables, and maybe you would have seen these in other thermodynamic classes also, right. So, I will not spend too much of time on that. Okay. Then the third important concept is that of equilibrium, right. Now, equilibrium is between system and surrounding. It is always that the system equilibrates with the surrounding, right. Now, what is a condition for equilibrium? Thermal equilibrium means T system should be equal to T surrounding, right. Mechanical equilibrium meaning P system should be equal to P surrounding. Okay. Then chemical equilibrium, and this is the most important thing that we have to look at in this course, right. So, this is thermal, this is mechanical, and this is chemical. Equilibrium means mu, or what I am going to just take one entire class in trying to understand what this mu is. Mu is called the chemical potential. Chemical potential of the system should be equal to chemical potential of the surrounding, right. It is possibly not always possible to define the temperature of the system, pressure of the system, but at equilibrium, right, it is possible to define these things, right. So, I am doing a cyclic thing here, right. I am defining equilibrium by saying system should equilibrate to the temperature surrounding, right, but I am also saying if system temperature, surrounding temperature are the same, if system pressure, surrounding pressure, and system chemical potential, surrounding chemical potential are the same, then the system and surroundings are in equilibrium with each other, right. So, then you say system and surrounding are in equilibrium. Right. Okay. So, that is the definition of equilibrium, right. Now, whenever we are doing thermodynamics, one of the most important thing is we are always seeking for equilibrium. Okay. We always want to go towards equilibrium. Now, the question is, if you always are in equilibrium, then what is the point of doing anything, because equilibrium is like a dead state, right. I am going to actually qualify it more, right. But equilibrium, if I am always at equilibrium, what is the point? I cannot grow anything, nothing grows at equilibrium, right. But you are actually studying the feasibility of it. You are saying that, all right, if I understand what equilibrium is, right, I know what far from equilibrium is. I have to take any system away from equilibrium such that it can come back to equilibrium, and in that coming back is my growth process, in that coming back is my material synthesis. Okay. So, for that, first of all, I need to understand this marker, which is the equilibrium, right, where system is equilibrating with the surrounding, right. At equilibrium nothing happens, no growth is happening, given, granted. But if I know what the equilibrium is, right, I can be at any arbitrary position and then assume that growth will happen. If I know what the equilibrium is, then I can calculate how far so I can take the system away from equilibrium by all these control parameters, and then so I leave the system there and the system will try to come towards equilibrium, and in coming to the equilibrium, that is when it is going to do all its wonders, it is going to make your material, right. So, if I have to give you an example, a mythological example, because Ramji had to go to Lanka, right, all that story has happened, all the Ramayana has happened, right. If Ramji was at equilibrium in Ayodhya, nothing would have happened, right. So, we would not be studying Ramayana now, right. In a very similar fashion, because the material has been taken away from equilibrium, right. So, because the system has been taken away from the equilibrium, has not been led to equilibrate with surrounding, that is when all these processes will happen. What process will happen? Again, I am coming to the laws of thermodynamics very soon, and so that is where all your material growth is going to happen. But I have to take it away from equilibrium, and for me to take it away from equilibrium, I should understand what equilibrium is, right. I should understand what Ayodhya is and how the dynamics were there at Ayodhya, to understand that he and his family had left Ayodhya, and so the entire Ramayana had happened. Okay, fine. Let us define something else, which is there are many thermodynamic variables, the state variables essentially, right. So, I am going to classify them as extensive variables and intensive variables, right. And extensive variables and intensive variables, one is size dependent. If the system size increases, the extensive variable, the quantity that describes this extensive variable also increases. The intensive variables are size independent. Okay. So, I am going to write it in a certain order. So, if pressure is the intensive variable, extensive variable is the volume. Volume of course scales with the number of molecules. If the number of size meaning the number of molecules, right. If number of molecules is large, size is that extensive variable scales with n, right. So, volume scales with n, of course, right. Pressure does not scale with n. I can have two materials with double, so one material has double the number of atoms as the material 2 has double number of atoms as material 1, right. But I can apply the same pressure on both of them. Both of them can feel the same internal pressures. That is perfectly possible, right. So, pressure does not depend on the number of molecules or so the size of the system. Temperature, and I am going to write entropy, which is what we are going to see what it is in the second law of thermodynamics. Then I have other variables like so if I apply an electric field, right, or so I am going to get some charge, right, and charge is an extensive variable, electric field is not an extensive variable. If I apply some chemical potential, the corresponding thing is n, of course n is extensive, and n meaning the number of molecules of that particular species. Okay. Now these two, right. So, if I apply pressure, I change the volume of the system, or if I change the volume of the system, so the pressure becomes an effect, right. So, these two bear a cause effect relationship, right. If I apply pressure, the immediate first thing that I do is I change the volume. If I should not change the volume, I should do some jugaad. I should change temperature, I should make sure that the equation of state is such that the volume does not change, but that is an engineering challenge, right. But the first thing that I will do if I apply pressure to this pen is I change the volume, right. Vice versa, if I am changing volume, how do I change volume? I have to generate some internal stresses or internal pressure. Okay. Similarly, I change temperature, ideally entropy, or so we are going to look at it as heat exchange, right. So, I have to exchange heat, right. So, between so two system and a surrounding, right. So, if I am changing the temperature, there should be changes in entropy. Okay. If I am applying an electric field or if I am applying an electric voltage, there should be a change in the charge that I am generating, right. Or if I put some charge on the capacitor, right. So, this is a parallel plate capacitor, I am going to put positive charges here and negative charges here, I am going to generate a voltage, right. So, they have a cause and effect relationship. Similarly, if I add more number of molecules or more number of atoms to my system, I am changing the chemical potential of that system, right. So, I am adding more molecules with the chemical potential of the system. So, all of these have a cause and effect relation. And hence so these are all called conjugate variables. These horizontal ones, right. So, these are called conjugate variables. Okay. Now, chemical potential, just leave it for now, I am going to again qualify it in a later class. I said I will take one entire class on just discussing what chemical potential is, right. So, so let us not pay too much attention right now. Okay. Okay, fine, that is good. So, with that we are now ready to look at the laws of thermodynamics. Okay. So, I will stop it here for this class for this lecture, and we can again take it up from the next lecture onwards, right. So, in this lecture we just we were actually trying to develop the language of thermodynamics, but in such a way that so I always want to relate it to the course that we are doing. I do not want you to get lost, right. Of course, you have to understand the language of thermodynamics, you have to understand thermodynamics, but it is easy to get lost of the final purpose. The final purpose is to make materials, right. So, synthesize functional materials. It is easy to lose that purpose, and so what I will be doing is I may be teaching things that seem trivial, at least in the first few lectures, especially for material scientists, but I am going to always relate it to the film synthesis, right, and so that you keep on internalizing it. When I think of system and surrounding now, I think of a film growth. I am not thinking about some abstract mechanical system and mechanical surroundings, right. So, I am not thinking about alright. So, this piston gas molecules are fundamental examples that are given in our 10th standard, 11th standard, 12th standard, right. But from a film growth perspective, so you can extend the same ideas, and then so you can think of an open system as my growth chamber. My growth chamber is an open system, right. So, this kind of correlation, if you make it at every point, that will be helpful as we proceed in this course. Okay. And just like I explained a bit of how e-beam evaporation works, I will be bringing in several techniques in different classes, right. So, they will relate to the course in that fashion. Okay. So, I am not going to specifically do a module of e-beam evaporation, molecular beam epitaxy, pulse laser deposition, sputtering, all these various techniques. So we will look at it under one umbrella of of this entire course. Okay. All right. So, with that we will again meet in the next class. Thank you.